In this problem, a wedge of mass m equals 40 kilograms is held in place on a fixed plane that is inclined by an angle theta equals 20 degrees to the horizontal. A force of magnitude F equals 300 newtons in the horizontal direction pushes on the wedge. The coefficient of kinetic friction between the wedge and the plane is mu k equals 0.2. Assume that the coefficient of static friction is low enough that the net force will move the wedge. The questions are: when the wedge is released and free to move, in part A, determine which direction along the plane it will move, and in part B, find its acceleration. Okay, let's solve the problem. We are given m equals 40 kilograms, theta equals 20 degrees, F equals 300 newtons, and mu k equals 0.2. First, we draw the free body diagram for the wedge. The wedge is represented by a point-like particle. The gravitational force is downward force and its magnitude is m times g. The normal force is drawn perpendicular to the inclined plane as this, where angle theta goes here. And finally, force F is applied to the wedge horizontally with an angle theta carried here. For convenience, let's decompose both m times g and vector f as we did in the previous examples. To determine the direction of motion of the wedge along the plane, let's calculate f times cosine theta and m times g times sine theta, since they are the only forces along the plane. They are F times cosine theta equals 300 newtons times cosine of angle 20 degrees, which is approximately 282 newtons, and m times g times sine theta equals 40 kilograms times 9.8 meter per second squared times sine of angle 20 degrees, and which is approximated as 134 newtons. Therefore, since f cosine theta is greater than m times g times sine theta, then the wedge will move upward along the plane with net force 48 newtons. In part B, we draw the free body diagram of the system after the wedge starts to move. In part A, we found that the wedge moves upward along the plane. Then, let the acceleration vector representing this motion be vector A as shown here. Additionally, since there is a motion, then there exists a kinetic frictional force denoted by vector Fk, whose direction is opposite to the motion, that is, downward along the plane. In order to find an expression for Fk, we first find the normal force. In this configuration, it has the magnitude with the same amount of the net force in this direction. Then it is n equals f times sine theta plus m times g times cosine theta. Therefore, Fk equals mu k times n, which is equal to mu k times f times sine theta plus m times g times cosine theta. To find acceleration A, we solve the Newton's second law, which is written here as F net equals F times cosine theta minus M times G times sine theta minus Fk, which is equal to M times A. We divide both sides by M and put the expression for Fk in this result. Then we obtain A equals 1 over M times F times cosine theta minus M times G times sine theta minus mu k times F times sine theta plus M times G times cosine theta. With the numerical values, we have 1 over 4 kilograms times 300 newtons times cosine of angle 20 degrees minus 40 kilograms times 9.8 meter per second squared times sine of angle 20 degrees minus 0.2 times 300 newtons times sine of angle 20 degrees plus 40 kilograms times 9.8 meter per second squared times cosine of angle 20 degrees. Finally, we get approximately 1.34 meter per second squared. So, we are done. Thank you for your listening and see you in the next lecture.